What's up, everyone? We're back from yesterday's look at the what was it, Vladivostok, which I'm guessing is somewhere in the Russian area. Uh, but yep, I said yesterday I was gonna work on getting uh, the assembly into something like Binary Ninja or some kind of assembler because I didn't really want to deal with going through all of the relocated code one instruction at a time. I ended up doing that, and we can see where we're at now and try to start working through the challenge. I'm gonna switch back over to the desktop. I'm all logged in this time. I did it ahead of time and made sure that we were good to go when I hit go. Um, so we're on this Vladivostok challenge right now, and we took a look at this yesterday a little bit. We kind of figured out what was going on. In the main function, all of this code is basically here to set up the relocation of the rest of the binary into some random location in memory. This rand right here is used to get that beginning address, and the second rand here is used for the stack. And there's a handful of operations that happen here to get them to ensure that they're in like a correct space and they're not going to overlap, involving like masking off bits and ensuring that it's safe. This mem copy here, we saw copies basically for 4,000 bytes, or 4096, 4K, and it copies from 4400 basically to the end of our memory space here. And then it will jump to the ASLR main, and we didn't really go into that yet because that's where it starts to kind of like fall apart, and it does all the things. But what we do know is that it zeroes out all the data so that this is no longer there. So we're not going to be able to just like typically like on embedded systems. They're not going to have ASLR, but like, if they did and they didn't zero it out, but like sometimes they'll have this look at the flash where flash is mapped into the memory space directly. Like you can just jump into the flash, and because you have that known address like where flash starts. In this case, we're not going to be able to do that for doing like ROP. We're actually going to have to defeat ASLR most likely, so that we can get ourselves to a position where we understand. There's a few ways to do that. Because everything is exec, like the stack is exec. Theoretically, if we can write onto the stack, and we can find a like jump SP or something like that, like maybe we can do that if that's usable. Actually, let's see what that assembles to. We'll put up the assembler. Jump SP. Can you not branch to register? DRSP. Okay. So it's a interesting enough. It's hex 41. That's not what I wanted. I wanted this. We might be able to find this just naturally occurring somewhere. And yeah, I mean, there's a few different ways you typically break ASLR. One of them is just brute forcing it. If you know how much entropy there is, then you have a probabilistic chance that you can land inside your address. With enough entropy, it becomes very hard. Sometimes you can find a leak, which we may be able to do here. Let's see, is there printf? So there is printf. Now, the unfortunate thing is, like, this isn't interactive, so like we'll have to basically like do this every time. If you're writing code to do this, like sometimes with printf, you can print out like addresses on the stack, and use that to leak the address of something, and then you can just kind of subtract because you know where it's all relative. We actually haven't run this yet and like done anything with it. I'm kind of curious if there is just a straight up format string vulnerability. We can try %x and see what this provides us. Interesting. So it looks like we do have a format string vulnerability in our username field. The password is probably going to allow us to have an overflow then, which we might guess as to how we actually defeat this is we're going to leak some kind of address from the stack, and then use the password to like just, overwrite our buffer. So I'm going to hit just send here, and we're going to continue. And what I instead want to do is I want to see like what we can get off of the stack here. So I'm going to do %x, 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 and see like what kind of data we can find. See if we get any kind of meaningful value. Yeah. So the second one here looks like an address. We could look at stack pointer. I guess we could look at A80C. That's probably going to be A80 FED C. So it's right here basically. A80C. So what we can do is we can do some subtraction here. A80C minus basically the beginning here, and see if we do this again, is that the same distance every single time? If it is, then we know that we can leak that value off of the stack, do that subtraction, and then do the defeat. I'm gonna go ahead and pop open Linux real quick just so we can do some math. So we're saying A80C. It may end up that this is really, really simple and we don't actually have to do a whole bunch of complicated reverse engineering. And I think what we've identified yesterday is the first byte ends up not being code. For some reason, it starts at 2. So I'm going to say, is it A4, A2. So that ends up being 874 bytes in. We're going to let it go for a second. It's super slow. X, %x. And we're going to hit continue. I also did less bytes this time in here, and I'm not sure if that's going to have an impact. So I'm going to try one more time if this matches up and just verify. Or if it doesn't match up, I'll do it one more time anyway. So this is our leaked address. And then we got to go find the beginning address. It seems like there's not a ton of entropy. And I think it's here. So 80F 4, 0, 1, 2, 3, 4. 80F4. Yeah, so that looks pretty reliable. We'll do this one more time. Continue. And we'll do %x, just like we did last time. So this, I think this ends up being a lot easier than I initially thought it was going to be, because it has this format string vulnerability that we can use to leak an address. And we're still going to have to find something useful to do with it, which means that we can ROP our way to success. We can look for like a branch a branch SP, and then maybe the stack pointer will point to something we control. BBAC. BBAC. And the beginning of our flash is at B842. B842. Yeah. So that's a reliable leak. We can leak a stack address. We can leak an address that is exactly 874 bytes from the beginning of flash, which is perfect. Then we just have to start looking for effectively gadgets that we want to use here. We also need to verify whether or not our input for our password ends up being in a useful place. So I'm going to do a couple things. First of all, I'm going to exit out of this and start up tmux. Microcorruption. Vladis. Oh, how do you spell this place? This. Oops. All right. So let's document this. ASLR is in place. We have format string vulnerability in from the username 2 words down the stack. Username stack is a relocated address. 874 bytes from the beginning of flash. So we now need to go in and we need to see like what we can actually do with the password. There's a chance we may need to use the %n to do an overwrite. I'm hoping that's not the case. We've already done some format string stuff in which one was it? This one, Addis Ababa. So we used the %n format specifier to overwrite addresses. Possible that we'll use it again. Maybe we won't. We basically need to go see like what this does. And unfortunately, so this is the shitty part is we're not really going to be able to debug this easily because all the code gets relocated. So let's look for what calls printf, basically. Let's toggle this back. This is all in printf, I believe. It's a huge function. And what's interesting is that like none of this So we can check if there's a format string vulnerability in the password. That would be one thing to know, so we know if we have that option there. So we're going to continue here. It's going to do its thing, which takes a second. 1, 2, 3, 4. What we can also do is look at our stack. We're going to continue, and we're going to do BB. And we're going to finish. So 4478. Let's pop open Binary Ninja. I did the work of getting this all set up. And so maybe this will be the fastest way to do this. Just so we can at least look at some disassembly. And do I have this saved? All right, XXD. There we go. Reset. And we're going to continue. Come on, come on, come on. All right, %x, %x. Let's leak our address. C404. What did we say the number was? 874? All right, so this is our new base. Our load virtual address is there. MSP 430. So what we're doing is we're telling it that the beginning of the address space is C09A, which is what we just figured out was the beginning. We're setting it to MSP 430. We don't know what the entry point is, but we don't really care. This is going to do its thing. I'm going to switch it over to disassembly because that's what we actually want. And then we're going to see where we are. So we're at 304. Oh, that's the that's the machine code. PC is at 10. We're going to single step. Oh. That's unfortunate. And we don't get call stack. So typically, like in GDB, you do like BT, and that would give you your call stack, so you would know like where you are, and I could just go like one below. In this, we don't. So we need to reset. We gotta do this one more time. All right. Let's do some quick maths. All right. This is our new base. We're going to rebase to that. And of course it's, oh, is it moved? Yep, it's back to high level IL, which is not what I want. Whatever. All right. Now we're at 88F0. 8. We're right here. And unfortunately, like we don't have all these defined out yet. I think this is ASLR main, I believe. We might end up going back and doing this. 10 is the trap handler. That's weird. Trap interrupt. We're at 88F2. F2. Is that the right instruction? Move R11 to R15. Yep. All right. How do I do this to make it as a character? It's display as character. Yeah. What's 896A? Moves R14. So this value into R13, compares it with 0. Not 0 goes to there. And this does the whole print thing. So it looks like they inlined like a bunch of stuff. But the nice thing now is we can I'm so like I don't know where the printf is. I think that this is that other ASLR main we saw. What the fuck is this? Some of this is garbage, like the way that it labeled stuff. I want to go back out to. I don't want graph view, just give me linear. I think I am going to fill in some of the functions here, just so that we can easily trace this. Let me rebase it back to 4400. Linear disassembly. I don't want that. Give me linear. Oh, whoops. Yep. It's a different procedure. Some of this behavior is really frustrating with it. Because I never like I don't want it to go back into the graph view. So this is init stack. After the bis. Oh, just the move, and then this. Wait. Init stack. Wait, why are you not? This is a new procedure. Right here. I'm telling you this is a new procedure. Undefined current, reanalyze, make function at this address. I don't understand like why it. Yeah. We get it, but build by procedure. So fine, let's 440E right here. And it just goes into the graph. Low level assembly. Attempting to add function not backed by file. What do you mean not backed by file? Stop it. Linear disassembly. I want disassembly. Let's try this again. Making a procedure there. And go back. And this is a procedure. This is a separate procedure. Like, why won't you do this? Fucking binary ninja. Like, so 4402. Is this even a function? 440. What? Why does there... What the fuck is this? Alright, let's undefine this. Let's undefine. Undefine. Alright. Like, I wish that, like, Binary Ninja had, like, a treat this as code, like IDA does. Where, like, I don't have to define a function yet. But I don't think it does. Decode. Yeah. Like, none of this is what I actually wanted to do. In the IDA, you just, like, hit, like, C. But we don't get that. I wonder if there's, like, a way to do this. Like, is it, like, can I go to key bindings? Transform. I don't know. But basically, we're at 4,400. So I'm going to show this in the procedure. This should be a separate procedure, which I can't do. Maybe I can't do it in graph mode or whatever, but this is right here. Why does it think it's going to R5 rather than... Oh, maybe it is R5. No, it isn't SP. Where the fuck did I think? Oh, below it. Okay. All right. I don't know what we just did and why that worked, but it worked. 4,400. This becomes init stack. This is a procedure, and it ends at this. And we're going to see differences in disassembly. This right here is move 0 into R15. MSP430 has this concept of like emulated instructions, which are basically instructions that that don't have different opcodes than other ones, but are like semantically mean something. So like the CLR opcode is an emulated instruction, and all it does is clear out or like zero the register. And so the opcode to do it is move 0 into the register, but this plugin for Binary Ninja doesn't understand the emulated opcodes, which kind of sucks because it means this is going to differ a little bit. We can see the test 15 is like compare 0, 15 because test just checks if it's 0. So little differences here and there, but we can deal with that. So I'm going to set up another procedure there. Fucking graph view. Like I don't want it to jump into that. This is low level init. this is the end of the function. This is the next one, the move32. Simply. That's interesting. 4424. Oh yeah. So do copy data. And then this one ends right before the call. So that means that this is main. I promise this will get a little more interesting in a second. I just need this to be in a meaningful state so I can actually do the disassembly. So this is do clear BSS. This is main. And then right below here, this is stop prog exec. What is this? 3, 4. Yep. This is CTOR's end, which we don't actually care about. This is ASLR main. This ends at 475C. Okay, cool. So this is correct already. This is ASLR main. Cool. And the next function, I think, is just ASLR main. I have the underscore. Yeah. That ends the ret. So that's correct already. And then this is printf, which is just massive. And ends 48EA. Yeah, so it's already correct. And now we just have to the ret, that's correct. So this is interrupt handler. Push. Where's the ret? 496. 4922. Oh. Get char. Hey everyone joining. I can give a little description about what I'm doing right now. We're going through the microcorruption game. I've pulled all the stuff out of here and put it into a format that Binary Ninja can read. We're getting all of this set up in here so that we can do our disassembly. This challenge is ASLR enabled, which means that it's going to relocate the data from where it starts to some random place. And we've already figured out how to defeat that. At this point, we just need to figure out what our payload looks like and what our overwrite is going to be like. Whether it's another format string vulnerability where we overwrite it, the return address on the stack with the format string, or whether it's a straight up just Stack Overflow that we can write enough data. But I need to figure out where the return address is on the stack in relation to our data we can write, so that we can figure out exactly like what we're going to end up doing. I think we just did get char. Get SN. This is puts. This is mem copy. This is B0. And this is rand. And I don't know if it has the last one there. It might or might not. Yeah, it does. This is just unexpected. All right. We have all this all set up now. We can jump around to the different functions, and we can rebase and get to meaningful addresses and actually track ourselves like through this. The whole point of doing this was that I wanted to be able to check where cross-references were. And the problem is, and this makes sense now that I think about it, is that all of the calls that we're going to be making in this binary, because there's ASLR, are going to be relative jumps. So this is using probably what's called position independent code is what I would guess like it is closely related to, where typically you'll see a call, we'll go to like ASLR main or something. So this is an example of a fixed call, where it's an absolute address. It's jumping to absolute address hex 10, which is 16. That's right here. It's trap interrupt. No, it's fine. So it's doing like a direct jump to there. Now, because this code is getting relocated, we have this problem where we can't use specific absolute addresses. We need to use relative addresses. So when it relocates this code, it copies, starting from whatever that is here. This 4400 hex, starting from here, it moves it somewhere else. It's moving this all as one. So what it's going to do is when it has like a call, it's going to say, well, I know that call starts 500 bytes from the beginning of the address space. So I'm going to basically load in, because the code itself knows where it starts. That data is passed. We saw that. Where is main? This right here. So it's passing in the start of the new address space, like where the randomization happens, into ASLR main. And so it's 35C plus the beginning is like whatever the function is. So it knows what the beginning is, and it can take that address and it can put the offset that it knows to figure out like exactly like where it needs to go. So we're never going to see a direct call to something like printf because it doesn't know. So like all this call stuff we see happening here, this like really complicated stuff, this is it trying to figure out like what the address is for the function that it wants to call. So I'm guessing that this right here ends up being our call to get SN. And then this probably becomes our call to printf. All right, spammers, it's time to get the fuck out of here. Sorry about that, everyone. All right, so we're gonna restart this, and I'm gonna hit C, and we're gonna leak our address again. It's doing its thing. So %x. So we now have. I'm gonna finish. This is it's going to be this minus 874. This is our our base address. So let's rebase. Of course, it's going to move back to the view I don't want. All right. So we can now go here. Our program counter is at 89B4. So 89B4. So yeah, this right here was the call to printf. A9B2? Yeah, because B4, we're at B4. So this is the printf. So we can set a breakpoint. It's so interesting that it has the. I wonder if it just is. It just knows because it's part of the instruction. So this is checking the length of the string. Compare byte to 0, so it's checking if it's if this string is 0 bytes long. If it's not 0, it's going to jump to here. And this is when it sets up the printf, most likely. We're going to copy the address there, and we are going to set a breakpoint. just break? Cool. And we can continue. And this should happen right before we print. So if I step into this call, we're gonna finish. We're at 8A to A. I wonder why it's doing the trap. So it moves, what's that, the stack pointer to SR, adds 8. So 8A to E. Then jumps back hex 24 bytes. 8A0E. What is it doing? Sorry, 1 second. All right, sorry about that. We are back. So I'm not exactly sure what this code is doing yet. But I mean, we can basically continue, and it's gonna hit that call again. Maybe it's waiting for input or something. Push PC. It looks like it's writing 2 bytes at a time. Or 1 byte at a time. All right, so it doesn't have the format string. It doesn't have the format string vulnerability in the password. So we know that it's just a straight up stack overflow because we never end up printing out the password that we entered. So we can do something pretty easy here. So I'm gonna reset. I'm gonna continue, get ourselves into a known good state. And we're gonna leak the address, %x, and I'm gonna continue. I'm gonna wait, and let's see here. We're gonna rebase, and it's gonna switch us out of course. So we're based now, and we know that we're in the interrupt handler, and we don't really want to be here. But we can look at where the stack is. And we should be able to see something right around here that looks like an address. So we're in here, where was wrong? So basically it's going to jump to here. It does this. I think it's main, basically. Main is the thing we should be looking for. Is so D4 A4 D4 C2 D4 2 6 1, 2, 3, 4. What's D4 2 6? Oh, you know what? Did I not do the subtraction? I forgot to do this. That is the real base. Disassembly. So most likely what we're looking for is right here, the D4 2 6. So D4 D4 2 6. So it ends up being right here. So once we exit out of ASLR main here, we can jump back. And what's interesting is we have this might be our jump SP. We're at what, D4 2 6? No, so unfortunately we don't have a zeros. Well, that's the large one. That's the small one. That's the large one. Yeah, this has to be swapped. Basically, what I'm looking for is to see if we have like a 4100 is what I'm looking for, because we found that assembler ERSP 0041. And and the thing is though, because instructions have to be aligned, we're gonna have to find this actually occurring. Like, I think if we end up putting it in the middle, it's going to say it's unaligned, and that's going to be bad. But we can look. What is 447E? That's not helpful. So we can try the unaligned opcode. I don't think it's going to work if we can find one. I'm not seeing a 4100 though, which is a problem. Basically, so this could be it right here. And that would be fixed, which is interesting. Yeah, maybe we could try this. So let's step. So we're there. Yeah, so that seems like it might work. Or the other thing we can do is we can look at our conditional unlock door. 7E, I believe, is not what we actually want. 7E, I think, is the HSM. Yeah, so 7F is unlock door, which is fine. Like, we can put our own shellcode in here. So let's write some shellcode. Push 7F call to do all this complicated shit. I wonder if it's easier for us to just increment this byte one. I also don't know how many bytes we can read. I guess we could figure that out, but we have some shellcode that's maybe position independent. Oh, it's only position independent because it's not position independent. Well, so it kind of is. These, we'll know the address. We might be able to do this. All right. Well, we can do a few different things. Let's verify that we can take control. I don't think there's a software breakpoint, unfortunately, that we can jump to, but sorry, 1 second. All right. So going back to here, basically our password needs to be 2468. So it's 8 bytes. Then we get to our return address. And let's see. %x, %x. So these are our 8 bytes. And then we want to do our jump SP, which would be 0, 1, 2. No, sorry. 1. So 1, 1. Yeah, so this is the fuck. This is that weird shit here. So BRSP. So I think that this is in little endian, but I can't, not sure. So we can try this. It'd be 1100. And we'll see if this allows us to do something unaligned. And our instruction would end up being I guess we'll just do the same thing. 0041. Yeah, so this is cool. If we end up doing this, we don't even need to leak the address, but I think that's why the leak is there. So let's get this ready just in case we need it. We're gonna rebase. Switch back. So frustrating. And then we're gonna step. Oh, this is so frustrating. We decided here we can set a new breakpoint. How do you get rid of breakpoints? in main somewhere. ASLR, this ASLR main. I think this is where we actually care about getting to, because it's going to fall through there at the end. Yeah, we're going to continue. It's going to print the password. It's going to continue. So all right. So theoretically, I'm gonna finish that. Where's all of our data? Yeah, so it ended up working. We're at 1-1, but the problem is that it needs to be aligned. So we're gonna have to give it like a real address for where our shellcode is, meaning we need to put shellcode on the stack. Or find usable ROP that's word aligned, which seems a lot less likely that we're gonna be able to find that within here, because there's only so many return points. But that's fine. So let's write some shellcode. The other thing that we can maybe do is maybe we can find I'm trying to decide if it makes sense for us to bother like trying to bump this up by 1 and then jumping to it, or if it's easier for us to just like write some shellcode. And I think that this is the correct function to call. I just don't know if these matter. Like what are they being used for? And that's so weird that like what the trap interrupt does. So all of this is still readable and writable and executable, I believe. So I don't think we have to worry about that. Extended the MSP430 to support software interrupts implemented with a call gate at address 10 hex. The MCU and the CPU executes the instruction at this address. The CPU begins executing special purpose block it pro code to perform special purpose functions, such as printing characters to the console or requesting terminal input. This interrupt kind is passed in R2. The status register on the high byte, the arguments are passed on the stack. Interrupts are described in section 4. The value arg must be in the range 0 to 7f. Inclusive. I wonder if we can just pass it in R2 and then just do it. Like this. This seems correct. Say we're going to do that. Move 7F R2. And just call I wonder if we can just do this. This might be too many bytes. It's possible, but we can give it a shot. Invalid hex, right. We don't want hex there. Finish. So we need to find a BRSP. It's so interesting though that I wonder if so I wonder if this is exact, like the offset between these. If it is, then it's easy. And once we leak the beginning of Flash, we've also leaked the stack. And then we can give a specific address. I guess the move is, let's see how many bytes we can write. This is 33 bytes. So we can't write 33 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we get 20 bytes total. We had 20 bytes total. How many bytes is this? It's 1, 2, 3, 4, 5, 6. We only need 6 bytes of shellcode. So like we could theoretically fit all this in the beginning of our string and then just jump to that. And that's not a problem. So let's see if this is deterministic or the offsets are the same every single time. So 6, 5, 7, 0, 59, 70, it's 30, 72. Oh, I didn't take into account that it doesn't start at the beginning here. So it's D4, D, E, D2, 3. That does not seem to be... Oh. Let's check this one more time and see. I think what we actually care about is the beginning here, because this is where the stack starts. I mean, it doesn't really matter because like we'll be within, you know, in order of magnitude. If it's like a couple bytes away, it's not a big deal. We can figure it out. But A6 D 0, 1, 2, 3, 4, 5, 6, 7, 8. And the beginning here looks like it's 9, 9, D 2. So let's see if we can do this one more time. It doesn't look like it's... We can figure that out from just that, though. So, worthwhile checking. It's E, B, C, E, B, 0, 1, 0, 1, 2, 3, 4. Yeah. So we don't have an offset from beginning of code to the stack. That's not fixed. It's possible that this is leakable. Can try adding some more, reading some more values off the stack and seeing if Like, do we see this on the stack at this point? Like the start address? Yeah, I don't. Oops. Yeah. So, not something particularly usable. So we don't know where the stack is. Yeah. All we're getting are 0 values there. So the only one that matters really is this right here, and that gives us the program leak. So 7E, we know that we can do so it's using HSM2, which is not super usable for us because it's going to pass the password, which we don't know. And we can't reliably return to shellcode because we don't know where the stack is. Well, we sort of know. So the stack SP is there. We could ROP this maybe. We can look for like a jump R11 or a call like R. All these call 10s are not good. They're not helpful because they're just calling the interrupt. Although yeah, I mean, like, ideally, we're gonna find like something that allows us to put something into R2. Like, is there like a pop R2? Because then we could put like. No, and this is the problem. Is like we don't have enough bytes to write like significantly past stack. So we can do what's called like a stack pivot, which is moving from the stack to somewhere else. But I don't know that we have the ability to necessarily do that. Doing this with the ROP is going to suck. Like really, really bad. And that's why it's important that we find a way to like leak the stack. So like this is where we end up getting to, I think, right here. This is where we end up returning to. And at this point, I don't know like what we have access to in our registers. But we can figure that out. Like maybe we'll find something that like our registers are set up in such a way already that we can find like a one gadget basically that does what we need. So let's rebase assembly. We see that the return address here is B8EE. Did it? B8. Wait. That's wrong? Yeah, that's very wrong. That should be the right address. Yeah, so this is where we end up returning to, and we can set a breakpoint there. And we can just continue. So let's see what's in our registers and what's going to be available to us when we get to this point. So we have B0AC, B0A, C would be FE, FEDC, B8F4. Not helpful. I guess we could find like an increment, R15 maybe by like 2 bytes. And call R15 or something. Is there anything else in our registers that is like helpful? B8, B0. Oh, B0, B8 points to the beginning of our stack, which we already know because it's the stack pointer. So So we can look for something that adds to R15, and then like, is there any kind of call to R15? Does anything meaningful with R15? P0. Yeah, it's like doing ROP is gonna be really hard. But we don't have a way to easily jump back anywhere. I'm gonna call R13. R13 is 10. What does this put us at if we add 10? It's 1, 2, 3, 4, 5, 6, 7, 8. That's pretty good. Can we find a add R? This is a good candidate right here. Basically, there's a call R13 at the bottom of main. Good candidate. So, can we find anywhere that is going to add SP to R13 and then return? R11. Not helpful. What the 4478 is. Oh, I want to return address from the beginning. Move R14 into 15. P0 AC. Add 2 to SP. Not helpful. Add 8 to SP. I guess the other thing that we could be looking at is these calls right here. That's the problem, is all these things are going to be adding to SP and not. Ret PC. That's not helpful. Maybe we can find what's an R14? B0AC. Yeah, it's not helpful. Just gotta find a usable gadget. Unless, so R15 into R14. Oh, they're already the same thing. Probably because of all that. Like none of these are like even close to like the 7F that we need. Yeah, I mean, there's gotta be a way for us to leak the stack or something. There's just not that many gadgets. I mean, we wouldn't have a lot of space. I think we found a way we can write 20 bytes. That gives us like what, 1, 2, 3, 4, 5, 6. So I guess we have enough that we could do some kind of ROP. I just don't know where we would, like what gadgets we would end up using. And that's the problem. Like, I mean, like all of these SPs pointing to 4478. To like R11. It's not even mapped. like we could theoretically return back into like main and use the format string again. And use like the %n if we wanted, but I don't know that that would help us. Yeah, so I don't see any 0041s, which is the shitty part. Like we can keep looking. What's 4400 do? That is interesting. BRR4? What's in R4? R4 is 0. Can we get a meaningful value into R4? That's not gonna be what we want. Do we ever use our fork at all? Move SP to R4. The only problem is that we're going to end up going into this function, which is not great. Okay. This could be good. Let's see if this disassembles correctly, if the endiness is correct. Continue. Okay, continue. I need to find the address of this. So FF. So it's FEFF. 1, 2, 3, 4, 5, 6. Oh. 1, 2, 3, 4, 5, 6, 7, 8. 16, right? No, it wasn't. It was 1, 2, 3, 4, 5, 6. It's 8. 1, 2, 3, 4, 5, 6, 7, 8. FEFF. FFE. And we'll continue. Why does it think that it's 3214? Step. What's 0044? So I don't quite understand why we are where we are. So, I mean, we're at FFFE. It thinks PC is there. But why did it decode 3241? The other thing that's interesting is why do these have our code in it? And is there a branch to R10 or a branch to R11? I think we saw some of that somewhere. So I'm really confused. I don't quite understand like why this is decoded as it is. This shouldn't be pop SR unless our disassembly like is wrong from here. But like the bytes here don't even match up. Like, I mean, let's reset this. Like we look at the, like this is the disassembly, and it's 3-1. Maybe it's not the disassembly. Oh no, it is 4400 3140. This is the next instruction. No, it's the current instruction because we're at init stack. So we're at init stack. Control it. Just fine. We're gonna leak this. Continue. 1, 2, 3, 4, 5, 6, 7, 8. F, E, F, F. That puts us at the last byte. Oh. Is that the last one before things get screwed up? What's an R4? R400, which in SN, so instruction address would wrap. I wonder if 00 is, yeah, so 00 is mapped. I don't know why I would wrap though. I guess maybe it is the other interpretation. I mean, the 0044. I mean, we can figure this out like real easily. We go to here and we do this. We can tell if it's handling the endianness correctly. Yeah, so 3041. So the way that this goes in is the correct endianness. 0044. Is this branch R4? Disassemble? Yeah, so I mean, so if we can find like a pop into R4 or some way to get something meaningful into R4, like we could theoretically so we can try this. So let's reset this. Let's leak our address. And then let's see if we can build a RUP chain. %x. Yeah. So finish. We've got our leak. We're gonna do a little math here. This is our new base. We're gonna rebase, and this is what we want. Is in what are we in? Is this printf? Yeah, it's the bottom of printf. We're gonna end up blowing away like basically everything. Oh man, but yeah, we're gonna lose like. Oh no, because they're moves. So that's fine. That's fine. Let's see here. So it's that. So it ends up being B0 DD. This is our gadget. And then it does all of these moves. SP, the stack pointer. I don't know what it's going to have now. It's going to have something in it. That ends up being FEFF. So let's try this. Finish. So we're in pop R4. Oh. Shit. The plus must mean that it decrements stack pointer, which is not what we want. Yeah, so that's not ideal. Pop R6, pop R7, pop R8. I mean, I guess this is like we could put like literally anything in any of these registers then. Like we had a call. I think we had an arbitrary call also. So we have a call, but we don't get R13 here. So these are all pops. Oops. So like 9, 10, 11, and then we're gonna ret, and it is, yeah, that's PC's at 0 because R4. RC is PC's at 0. Because it ended up returning to 0. So yeah, we would have to get enough on there. Man, that is so frustrating. Give me a second, I'm gonna get some more water. Hey, unfortunately, I gotta wrap things up a little bit early. I've got a dog here that wants some attention. But I think we'll pick up to maybe tomorrow where we are right now, and hopefully wrap this one up. I hope you all learned something, and we'll get back to this and finish it. I'll see you all next time.